Hey, AP Chem, we are going to be working on something called the enthalpy of solution today. And honestly, it's pretty much just calorimetry, but instead of talking about an object, we are going to be talking about a chemical that is dissolving. In our next lesson, we're going to get into specific chemical reactions because those are a little bit more complicated. So I feel like I'm kind of like trying to wade in a little bit more difficult each time. So we're starting with solids. Then we're going to get into calorimetry with solutions, which is a little bit more work, and then we'll get into chemical reactions. So just kind of baby steps as we go along. So like we talked about with looking at a solid going into a solution, we talked about how if we take a hot object and put it into a calorimeter full of water, the hot object is going to lose its heat out into the water. And those two values, because of what we call the law of conservation of energy, those two values should be equal to each other, but opposite in sign. Now, when we talk about putting a chemical into a water-filled calorimeter, that is the dissolving process, which we talked about a lot when we talked about intermolecular forces, but that process can itself be endothermic or exothermic. And when you think about the chemicals when we are doing this process, you have to think about them just kind of like the object. So if the water is gaining heat in your calorimeter, that's because the process for the dissolving is exothermic. And what happens is, as a consequence, the surroundings have an increase in temperature. And then the opposite situation is the case when we have something that's taking heat in from the water, and that's going to be an endothermic process. So endothermic processes pull in water, and your water temperature is going to go down. Exothermic, your reaction or dissolving process is going to put energy into that, into the surroundings, and the temp goes up. Okay. So hopefully that makes sense to you. Now, when we talk about something dissolving, there are actually kind of three parts that go into this process. And we, like I said, talked about this a little bit with intermolecular forces and lattice energy. But when we talk about something dissolving, there are always two endothermic steps and one exothermic step. And the two endothermic steps are this. When you put a solute into a solvent, the solvent itself needs to expand to accommodate for room to take the solute particles in. Additionally, the solute itself needs to come apart and then make room for the solvent to surround it. So both of those steps, because we're kind of pulling things apart, are energy requiring steps, thus they are endothermic. And then when we pull those things apart, we're overcoming things like the lattice energy or the hydrogen bonds or whatever, and all of that requires some energy. But what happens then is when those things come back together, there are new intermolecular attractions that are formed between ions and the solvent, or if not ions, then a different type of intermolecular force and the solvent. And when you do that, you get a solution. And when that requires more energy to put in than you get back out, it's an endothermic heat of solution. And when you get more energy back out when you make that solution, it is a exothermic heat of solution. And so it's kind of just like we talked about before, where the amount you put in, if it's more in than out, it's endothermic. And if you put less in and get more out, it is an exothermic process. Okay. So like I said, two endothermic steps: expansion of the solvent, expansion of the solute, and then when they remix together, that is an exothermic step. So it's just essentially going to be calorimetry that we are dealing with. And when we talk about heats of solution, more often than not, they're going to talk about something called the molar heat of solution. So we're going to do an example problem, and I'll show you how to do those calculations. This problem that I'm going to show you is probably worded in a more condensed version than an AP FRQ. So an AP FRQ is going to probably ask you to do a couple individual steps and then tie it all together. And we're just going to kind of do it all in one fell swoop here. So if you look at the example, it says when 5.5 grams of ammonium nitrate is dissolved in 100 milliliters of water, the temperature of the water decreases from 21.5 degrees Celsius to 18.3 degrees Celsius. Calculate the molar heat of solution of ammonium nitrate in kilojoules per mole. Assume the specific heat of the solution is the same as water, and is the reaction exothermic or endothermic? So if I get my dot cam up here, like we always do, here is our example. Now, this, because like I said on the exam, they'll probably break it into smaller pieces. There's a lot to digest here. So what I really recommend doing is drawing a picture like I always say we should. So I've got 5.5 grams of ammonium nitrate dissolved in 100 milliliters of water. So here's my calorimeter. My calorimeter has, let me change my focus here. Otherwise, this is going to be a lag in my voice, and it's going to be super annoying. Okay, that's better. So anyways, if I put my chemical into here, I've got 5.5 grams of my ammonium nitrate in here, and I've got my thermometer that's going to be measuring my temperature. And if we look at what happens to our temperature, the temperature is going down. So if you think about the energy process or the change that's happening here, if the temperature of the water is going down, what that means is that that energy must be going into this particular chemical to make that change happen. So when you think about the process, if the chemical is absorbing energy, that means the reaction is going to be endothermic because the exterior is getting colder. Okay, hopefully that makes sense. Now, this is a little bit different than our metal calorimetry piece because it's asking us to calculate molar heat of solution in kilojoules per mole. So a couple of things to think about. The kilojoules obviously need to come from some sort of heat equation. We are going to need a Q there. The moles, though, is a little bit tricky. Is it the moles of the water? Is it the moles of the chemical? Is it the chemical and the water together? What is it? In this case, it's moles of the stuff reacted. So it's the chemical that's causing it. Remember, the water is just a reflection of what's happening, but the chemicals actually cause it. So it's going to be over moles of NH4 NO3. So we've got kind of two things we need to figure out here. We need to figure out what the heat is, and we need to figure out how many moles of this stuff are going to be reacted. So when we look at our equation here, we got to figure out our Q. That'll be our first order of business. So we know Q equals M times C times delta T. And they tell us that our temperature change is here. They tell us that specific heat of water is the same as the solution. And they tell us the mass of stuff in here. Now, because these things are interacting and the thermometer is in a mixture of the two of the solute and the solvent, in the case of a reaction where everything is mixed together and it's not in its own separate container, we have to take the mass of the liquid and the solid together. So our mass is actually going to be not 100 grams like it usually was. It's actually going to be 105.5 grams of solution because it's this water and the chemical together. My specific heat is 4.18 joules per gram degrees Celsius because it's the same as water. And then my change in temperature is going to be T final minus T initial. So 18.3 degrees Celsius minus 21.5 degrees Celsius. And you can see in this case, it's going to give me a negative temperature change. We actually drop 3.2 degrees Celsius. So when I put these into my calculator, I am going to get an energy change of negative 1,411.71 joules. Now we got to get this into kilojoules here, right? But here's what you have to think about, and this is weird. The negative value is for the liquid that we have in our calorimeter. So makes sense since the liquid is getting hotter that we have since the liquid's getting colder, that we have a negative value. But we are looking at what's happening in the process. So just like the piece of metal, if I have a negative value for what's going on in the liquid, the process here must have a positive value. So when we think about doing our division, we are going to have a kilojoule value. So this is negative 1.41 kilojoules. So I'm going to have a negative kilojoule value, but when I put it into my kilojoules per mole, I have to remember to turn this sign to a positive sign. And you're going to have to do that with anything where there's a chemical reaction happening. So just make sure you watch the signs. The other thing we need to do is we need to get into moles of the ammonium nitrate. Okay, so that's our next order of business. And I have 5.5 grams of ammonium nitrate. And the molar mass of that, I'm not going to show you how to calculate because you should be able to do that already. The molar mass is 80.052 grams. And when I get that into moles, I get 0.0687 moles of my chemical that's causing this change here. Okay. Now, a couple things that I've noticed. Don't round this off. So don't round this to 0.07 moles. I have 3 significant figures here. I have to keep those here because when I round it, this is such a small number, it causes a pretty dramatic change in my overall ratio because it's such a tiny number that I'm dealing with. So now when I want to get my heat of solution, I'm going to take my energy, but I'm going to remember to turn the sign positive to 1.41 kilojoules because this is for the liquid. This is the chemical's gain in energy. And I'm going to divide that by 0.0687 moles, keeping the significant figures correct here. Okay. When I divide those two, I get a positive 20.54 kilojoules per mole for my enthalpy of solution. So what that means is that if I would dissolve a mole of my stuff, I would release 20.54 kilojoules worth of energy in the process. Oh, I did it wrong again. I will absorb 20.54 kilojoules worth of energy. My water's going to lose that. Okay, so the water is going to release that into the chemical. Now, when you look at this problem here, if I would have a higher mass of chemical that's doing this reaction, let's say I had twice as much chemical, I would generate twice as much heat in this process. So the heat that's coming from the water, it would be double, right? So if I had 11 grams, it would take 2.8 kilojoules to make that dissolve. But what's going to happen then is when I calculate my number of moles is also going to be double. So I would have, and I'm just quick doing the math here, 2.82 kilojoules, but it would be divided by like 0.1, quick math here, not good, 0.13 something. So I'd have twice as much energy, but I would have twice as many moles. And so the ratio should stay pretty darn close to the same. Okay, so things to watch out for. You got to switch the signs. And when we are doing the mass of our solution, it's the combined mass here. And then our moles is just the chemical. A common error I see people making is that they say it's 105 grams here, but that's not all the chemical. A lot of that's water and it's not doing anything. So if you have any questions, please get things cleared up. Otherwise, you're going to take a crack at your homework and see how things go. All right? Good luck.